everyone, my name is Patrycja Wegrzynowicz, and today I'm going to tell you about security, or rather insecurity, of JSON Web Tokens. First, a short introduction. I've been doing professional software development for over 20 years. Currently, I'm a senior platform engineer at Form-Free Financial Cloud. As we deal with financial data, security is very important to us and is built into our software development process from the very beginning. My general interests focus on patterns and anti-patterns in software. I used to work on tools for automated detection and refactoring of software defects, such as performance anti-patterns, database issues, and last but not least, security vulnerabilities. So basically, security has always been present in my daily job. What am I gonna talk about today? First, a brief introduction to JSON Web Tokens, just for all of us to be on the same page. The key part of today's talk involves 4 demos that reveal some problems with security of the spec, the implementation of token libraries, and some problems with our applications. If you have any questions, I will handle them in the end of the talk. There are a number of caveats related to JSON Web Tokens, and we'll start with the very first one and very difficult one, which is how do we actually pronounce it? And it turns out it's not a piece of cake. As a native Polish speaker, I pronounce it as JWT. In English, I usually hear the pronunciation as JWT, but the RFC suggests the same pronunciation as the English word jot. By the way, jot in English means a brief informal note, just as JSON Web Tokens are short, less formal tokens. However, in today's talk, I pronounce it as JWT. Why? Because simply it's the most popular version in the software world. Plus, I'm not sure whether I pronounce JOT clearly enough. So JSON Web Token is a set of claims that encode user's identity and usually user's permissions. It also consists of a digital signature to protect its content against tampering. It's always handy to take a look at some sort of an example. We see that a JSON Web Token is a long string consisting mostly of letters and numbers. But when we take a closer look, we can recognize 3 separate parts separated by dots. These 3 parts are a header, payload, and signature. All 3 base 64 URL encoded. When we decode these 3 parts, we see that a header and a payload are just JSON strings. The header contains an algorithm used to generate a signature. In our example, it's HS256, HMAC with SHA-256. The payload contains the actual claims of a token. In our example, it contains 4 claims: subject, issued at, issuer, and expiration. And signature is just a binary content. Here we also see the very first problem of JWT, the lack of confidentiality. The tokens are not encrypted, they are only encoded. So it's easy to decode them and see all data data available in claims. Therefore, we should avoid enclosing any confidential information in claims. JSON Web Token is generated on the server side, then it's stored on the client side, usually in the session storage. Then, with each subsequent HTTP request, the token is transmitted to the server, usually as part of the authorization header. Then, on the server side, the token is verified, and in case of an incorrect token, the request is rejected. It sounds very simple. So now it's time for the reality check. Let's take a look at some security problems of JSON Web Tokens. Before the first demo, some organizational information. I will need your cooperation during demos. I would like to show a live hijacking of your accounts. So my kind request to you, please go to the demo application, the link available at my Twitter account, YonLabs, and also you can see on the screen. Please register your account and log in. So now it's time for the first demo. The first demo reveals a problem with the none algorithm. In JWT spec, there are only 2 mandatory algorithms to be supported by a library. The first one is HS256, and the second one is none. None basically means no algorithm, thus no signature. In my demo, I will show you how to use the none algorithm to bypass server verification. Okay, now I will log in to my demo application. If you go to my Twitter, you can see the link on Twitter. Oops. Some problems with internet connection. Hopefully it will get sorted. Okay, you can see the link. Please follow the link. In the meantime, I will show you the application. I will log into my application. First, you need to register. Don't use any significant username or password, just fake data. Remember, that's a security vulnerability demo. It's a simple application displaying profile and the list of users. Oh, I see a lot of you have already registered. Nice to see that. We can see that the JWT token is stored in the session storage. I can see my token. If I copy a token and we'll go to JWT.io webpage, I can see that this is HS256 token. It contains 3 claims and some signature. Okay, so now I have some fake signature prepared. That's the one. It uses non-algorithm, and the user ID subject claim from the token is free. So I will copy it, and I will just replace the actual token with my fake one, and I will hit refresh. What happened? I'm now logged in as error. Congratulations, error. Your account has been hacked. So that was a very simple demo, and you can see how simple it was to bypass server verification. Why was such a token accepted by the server? Because we have a vulnerability in our code. And unfortunately, it's a mistake one can make very easily. What's the mistake? At first sight, our verify method looks fine. However, it's not. We've used the parse method, which only decodes the token and does not verify a signature. So instead of parse, we should use parse claims JWT from JSON Web Token library. It depends on the library, so you need to verify the details of your library with the manual and the docs. And in case of this library, I must admit that the naming is not very intuitive. So it depends. As developers, we need to, unfortunately, take a deeper look at the docs of the libraries and frameworks we use. And it's not the only library with the none problem. When we search the National Vulnerability Database, we can find many more issues related to JSON Web Tokens. One of those issues reveals the non-problem in another library, albeit much less popular. And check out the year of the entry. The issue was raised in 2018, so it was okay 3 years ago, but still I'm wondering how many applications are not patched yet. Who knows? There are 3 main problems revealed by our first demo. The first problem is the presence of the none algorithm in the RFC. I guess that the intent was to use the none algorithm in a controlled environment like internal network. However, even in such cases, it's not recommended from the cybersecurity point of view. The second problem is the misleading APIs in JWT libraries. And the last but not least problem is with us, developers. We often don't read manuals, we use samples found in the internet, so such mistakes happen. And actually the code I've shown you, it was found on GitHub in some repository that was using JSON Web Token library. To protect our code against such problems, we should understand a library we use. We should check out vulnerability databases. And additionally, in our code, we should require a specific algorithm and a specific key during verification. Why should we require a specific algorithm and a key during verification? Because otherwise, we can end up with serious security vulnerabilities in our code, like this one. When a hacker can trick a vulnerable application to change the algorithm to HMAC-SHA instead of RSA. Let's take a look at the attack scenario. For a regular user, the server generates a token signed with a server RSA private key, and the server verifies a sent token with a server RSA public key. For a hacker, the hacker generates a token signed with a server RSA public key used as an HMAC secret, and then sends a request to a server changing the algorithm to HS. Then server, when it verifies the token, it uses the algorithm in the request from JWT token sent by a hacker. And the server uses its public RSA key for verification. So the verification can be successful in such a case. And here's another reason why to require a specific algorithm and a specific key. It's another vulnerability where a hacker can provide his own public key for the server to verify a token. And actually, the library followed the standard, and that was the root cause of the vulnerability. The standard specifies that a JSON web key representing a public key can be embedded within the header. That's another problem with the standard. The main paradigm of cybersecurity is never trust a client. So the attack scenario and in this case is that for a regular user with server signs JWT with RSA private key and verifies with server's RSA public key. But when a hacker provides a spoofed token and provides his or her own public key in RSA header, signs the token with his or her private key, then the server uses the provided public key for verification, thus the verification succeeds. Let's move to the second demo. The second demo is a demonstration of a key cracking of HS256. HS256 stands for HMAC with SHA-256, hash-based message authentication with SHA. The algorithm requires a secret key. It's a symmetric algorithm, which means the same secret key is used for generation and verification of a signature. As this is a symmetric algorithm, once you get to know a secret key, you can generate your own tokens to be accepted by the server. So for this demo, actually I've rented a GPU-powered machine. We can take a look how it's configured. Basically, it has two pretty powerful GPU devices. That's GeForce RTX 3090. Those are plus a CPU. For passwords, Hashcat is a free and open source password cracker. Or, sorry, rewind, it's not a password cracker. They call themselves a password recovery tool. So Hashcat uses very highly optimized brute force algorithms to crack various kinds of encryptions. And they use GPU for that purposes, and it's much faster than with a single CPU. So for our demo purposes, first we need to grab a real token. So luckily, I have an account. I will get a fresh token. We already know that this is HS256 token. And I have a simple script prepared just to provide a token to Hashcat and provide some parameters to choose JWT and brute force attack as a cracking method. Let's wait and see how much it takes for Hashcat to crack this password. What's the, oh, that was pretty fast, around 10 seconds. And we can see that the speed of password cracking was like almost 3 billion hashes per second. So we can see that the password, our secret, is simply JCON29. And now I need to generate another token to impersonate another user. And I can simply hijack another account. So once we know our secret, we can use again JWT.io site to generate another token. This time we'll use, for example, subject 9. That's our token. And we just replace the actual token with the generated one. Let's do it once again. Okay. And now hitting refresh. And now I'm logged in as GBG. Thank you for your cooperation, GBG. So we can see that GPU dramatically improve the cracking speed. You can compare the left side, which is my laptop. It's only like 5 million hashes per second. For another instance with 2 GPU processors, 2 GPU cards, it was like around 2 billion hashes. In our case, it was 2.5 billion hashes per second. So pretty fast, and that was only 2, but pretty powerful GPU cards. So what was the problem, or what were the problems revealed by our second demo? The obvious problem is the weakness of our secret key. Another problem is that for the key cracking, the hacker needs only 1 token, and all cracking is done offline without any communication to the verification server. Therefore, there is no method to detect such brute force attacks, and a victim remains unaware of the attack. And once a hacker knows the secret, he can generate whatever token he desires, impersonating whatever user he desires, and he can generate as many tokens as he wants. So that's a huge problem of our second demo. It turns out it's pretty complicated to adjust our keys and algorithms properly, as there are many algorithms and different kinds of keys possible. There are 4 main algorithmic families available. The first 2 are the most popular: HMAC with SHA and RSA with SHA. As it comes to HMAC with SHA, the recommended key length is as long as the length of the hash. So for HS256, at least 32 bytes. It's worthwhile noting that it's a symmetric algorithm. So the shared key is used for generation as well as for verification of the tokens. Therefore, the secret key must be present on each server which performs verification. So when one server is compromised, the entire system is compromised because once a hacker knows the secret, yeah, we know he or she can generate any token. In case of RSA with SHA, the recommended key length is 2K bits at minimum. RSA is an asymmetric algorithm. It uses separate public and private keys. Only authentication servers possess the private key, and verification servers use only public keys. So therefore, the attack surface is decreased in case of the scalable infrastructure with many machines. Let's move to our third demo. In this demo, we will switch to HTTP. I will post an HTTP link on my Twitter account. And please use this obviously unsecure means of communication just for the demo purposes. So I'm gonna steal one of your tokens by packet sniffing. But first I need to log to, actually I'm logged in to my server hosted on Oracle Cloud, and I run TCP dump. I prepared a simple TCP dump script, just a shortcut to some pretty complex TCP dump parameters. I'm trying to capture all traffic on port 80, and I'm grabbing for bearer token, just to be easier for me to copy of one of your tokens. So I will run TCP dump, and my kind request to you, oh, you are very fast, a lot of tokens coming in. Okay, so I will copy this one, and that will be a surprise. Who will be hijacked this time? So again, I will just log in with my account. Oh, it seems my password is very secure and not stored in my browser. So I suppose I need to register a new user. Okay, I will log into my new user and see the token, but I'm going to delete it and replace with one of yours. So refreshing, and Jonas, thank you. You are very fast, and one of the very first tokens coming in. So obviously the very first problem of our third demo is the lack of encryption. We should always use HTTPS, and the HTTPS should be used consistently. And another problem is that stolen tokens can be freely used as long as they are valid. So we need to pay special attention to expiration times of our tokens. The problem in our previous demo was the lack of encryption. So let's move back to the encrypted communication channel. Let's use HTTPS. and still I'll be able to hijack your session. This time by exploiting an XSS vulnerability to steal one of your valid tokens. So I'm moving back to my demo application. We can see that we have a simple profile, and we can update our homepage. But I have some special script prepared, XSS and tag, which just loads retrieves the token stored in session storage and sends it to my evil server. Plus, it displays some simple alert, just to be a nice hacker, that your JWT token has been stolen. Okay, so this is me exploiting XSS vulnerability. And now you can see that demo has this special link. So my kind request to you, please click the link on the demo account, and I will log into my evil server this time already, and I will observe logs. Okay, so a lot of stolen parameters coming in. Oh, I need to stop it because I can't copy anything. Okay, this one. And we'll see whose token it is. So, Marcel, thank you. That was your token. Congratulations. You've been hijacked. So, let's move back to the presentation and let's take a look at our attack vector. The only tricky part of the malicious JavaScript is that we do not connect to the evil server directly. We connect via loading the link as an image source. This way we bypass same origin policy implemented in browsers. And there are many more validations or verifications implemented in browsers nowadays. For example, Chrome doesn't allow to mix HTTP and HTTPS. And if you take a look at requests issued by browsers, by Chrome browser, the HTTP in this link has been changed to HTTPS. Fortunately, my evil server, this is just a simple server that logs down all incoming parameters. Fortunately, my evil server serves HTTP as well as HTTPS traffic. Obviously, the core problem of this demo was that our application has an XSS vulnerability. So we should apply the best anti-XSS practices. And the problem is there is no other way to block access to a session storage for JavaScript. So when we use session storage, JavaScript can always access the token. However, we could use a hardened cookie as a storage mechanism for JWT. Hardened cookies use such flags as secure, HTTP only, and same site. So in case of hardened cookies, JavaScript can't access its content. But we fall into another trap, which is we need to be protected against CSRF, cross-site request forgery. So there is another way to protect against token hijacking. OWASP, which stands for Open Web Application Security Project, provides a solution based on a random secure value sent in a token, as well as a hardened cookie. If you want to know more, please read the explanation in a OWASP cheat sheet. Basically, OWASP has a lot of valuable resources when it comes to security for developers. So I highly recommended project and web page. So we see that that our demos were only the tip of an iceberg when it comes to JWT security. In addition to algorithms, implementation, protecting against eavesdropping, XSS, etc., we should consider also logouts and timeouts as basic hygiene for safe applications. Unfortunately, JWT does not provide any built-in feature to revoke a token or expire token after inactivity period. So again, it's up to developers to implement those things correctly. So again, even though JSON Web Tokens are self-contained and stateless, the state strikes back because we need to have some sort of a persistent storage to validate a token against expired tokens, not expired tokens, against invalidated tokens. Like during logout, we should, on the server side, mark the token as invalidated. So unfortunately, it's not very easy to get rid of the state in our applications, and then the scalability becomes an issue once again. And a piece of advice here, remember, a fool with a tool is only a fool. We, developers, can't be fools. We need to know how to use our tools wisely. And in software development, we have continuous integration. We have continuous delivery. I always talk about continuous refactoring to keep our code clean, but the fundamental paradigm is continuous learning. So as developers, we must keep learning. So that's all for today. Thank you. That was very, very nice cooperation. You've been very active and you've been part of very successful demos. Now it's time for your questions. Looking forward to that. Yes, XSS is mitigated by I see a couple of questions on chat. So how did this JS injection work? I can show you the code. Maybe I will share my screen once again and show you the actual code of JS injection. Basically, it happens when the developer doesn't encode special entities in in any data which is provided by a user and then displayed again on a web page. So in my case, I've used Angular, and let me find the actual view, and I had to use some some insecure method of Angular. Wait a moment, I need to find it out, and it's pretty. That's a user. We have the username. I don't see it at the moment. Basically, JavaScript injection happens in every page. Here we have like displaying of a user. By default, most modern libraries provide some sort of user of encoding of outputted values. So in many cases, it's done by default. In some sort of frameworks, like older frameworks, like for example, the old Java servlets and JSPs, you need to take care of that yourself. But still, in such cases, in case of modern frameworks, you need to you can use some insecure methods and provide some output directly. Yep, that's one. Thank you. That's the one. And when we take a look at this bypass security trust URL. Using digital certificate and non-simple password, is it very more secure? If you use them only for authentication, it's basically the same problem, because the main problem is where you how you maintain session. So if the session is maintained via JWT, we end up with the very same problem. So it depends on the way how the session is maintained and passed between user and server. XSS mitigated by CORS? Not exactly, because in our case, we accessed an external server, like we accessed evil server. XSS can be mitigated by content CSP, content security policy. That way we can limit the number of web pages to the specific web pages which we can hit from a client browser. So that's a good anti-XSS policy, to use very narrow content security policy. Okay, so very interesting. Why is the modified token with Patrycia's secret valid for user 9? That's the basic property of JWT, and it has nothing to do with hashing password assault. Basically, we rely on the token itself and the claims contained in the token. So basically, we usually rely on some ID as a subject. So we can switch ID, and once we know secret, and we can generate a valid token, then we can impersonate any user. Okay, thank you very much for your question. If you have more of them or you want more detailed explanation, please write on Twitter or reach me via email. And thank you very much for your active participation.